Alright, this is what I've been leading up to. We're going to do a heavy cut, 1 1/8 with this monster. And we're going to have all this electronical gear on here. Safety first, of course. Got some Elec Chickens tape on there. What for keeping the 1s and 0s in. Don't want those magic pixies. Gentlemen, welcome back to the shop. Today we got our Festool basket case. We're layered up too deep on the workbench here. There might be a little project creep, but we're going to get this back together today. We're going to test her out, flog it like a rented mule, and post the video about it. If I can get the fucking thing back together. I seem to recall I was a little bit more bold than China Shop the last time I had a look at this. I do not remember. Fuck all. I'm pretty sure this is not part of it though, so that's a start. Okay, before we get this together, and I just want to say, this is, yeah, I'm not looking forward to this because I got a feeling I'm gonna fuck something up. But I suppose if some disillusioned German almost pensioner can put one together, I might be able to have the wherewithal. That's that whole thing from that movie, right? If one man can do it, another can do it. That's where we're going with. I had a thought, however, before we put this together. I just got this stuff recently, and I'm still getting my head around having this in the toolbox. This is awesome. It's magnetic field viewing film. You can see magnets with this. So, this is a magnet. Let's have a look. Look at that. It's diametrically magnetized, but it's not just two poles. It's a whole bunch of poles. So if we go ahead and count how many poles, there's 1, 2, 3, 12. 12 poles. Now, say this universal motor turns at 25,000 rip ohms. I just want to do this because it's interesting to me to see how amazing our microcontrollers, electronics, dumb as fuck, right? But they are so good at counting. And essentially, if you can break any tasks down into counting, or on a higher level into mathematics, computers do it so fast, it's incredible, but dumb as a post. You know, you ask one to peel a banana, never gonna happen. So we've got 12 poles. This is turning at 25,000 rip ohms. 12 times 25 is that'll be 300,000 rip ohms per, well, revolutions per minute. Now you divide that by 60 seconds in a minute, that's going to be 5,000. This is counting 5,000 times a second like it ain't no thing. It's monitoring the position of this thing. Incredible, incredible. I beg your pardon for my brief nerdgasm. I'm going to go ahead and slam this back together. I will save you, for the sake of brevity, I'm going to save you from the verbal assembly lube. That is the cussing and the spitting. Through the magic of YouTube, this will just be assembled and we'll go ahead and test it. I'm starting to think about putting this thing back together, and all the old horrors come flooding back, the memories. You believe this? Cheesy grease? It's all separated already, like all the liquids leaked out of it. Pretty schmoo-like. I got axle grease here that's probably older than some of you guys watching. It's got to be at least 2 decades. It's not separated. And in case you're wondering, boingy boingy, fixed it-er. Manok Jongi would be proud. And just looking at this is cute here. These 2 little sense wires that goes into the board. These red wires. It's on the field. It must be either a thermistor or some sort of temperature sensor to tell the microcontroller to shut down if it gets too hot. But that is on the field, mind you, not on the brushes or anything like that. So, well, this little widget here had me licked. Spent 15 minutes friggin' and fucking trying to get it in the right spot. I don't know what it does or where it goes. So, I'm afraid, gentlemen, you gotta know when to fold them. I had to cheat. And apparently goes in the handle, but a different way, and there's the spring thing. Yeah, but the wonder of the internets, am I right? Part stack-ups right online. Lo and behold, this little choocher here is the blade lock, and you've never seen anything like this. What happens is the blade lock, it's got this little nub on here, it bears on the fan. So when you when you press it down, it locks on the fan. Are you kidding me? Bear in mind, that's plastique. Anywho's, it's once again for the second time. Maybe the fifth time. Now, I don't know if I filmed all that because the camera might have done its outer space routine there. But, holy, this mechanism is just, it's really like beyond the beyonds. Engineer's wet dream. The poor bastards that have to put this together in the factory. There's logic gates. It's a mechanical computer, like a Pascaline 1916 French mechanical confuser. It's just ridiculous. There's logic gates and pull-ups and tensioning springs to pull down and interlocks, and holy moly. If you ever take this apart, don't do what Donnie Don't does. Well, first of all, you don't want to ever take it apart. That's what I'm here for, right? But don't do what Donnie Don't does. Make sure you take a picture or something, because this ain't gonna cut it. Oh, and hey, look what I found. The field winding fasteners. Yay. Now the whole thing's got to come back apart. Oh my god. So this is like the 18th time I've had it apart. This is no fucking good at all. Starting to get a little bit frustrated. Why the fuck does this not go on? Whoa. I think it was Abner Weinstein that said, make the thing only as simple as it needs to be, but no simpler. Holy. This thing's... Wow. Okay, well that was fun. That's, yeah, the kind of fun that's best left to somebody else, if you know what I'm saying. Back together now. And we're just putting a target on there. What, for checking the ripplings? And we'll do some electrical testing. I'll hook up the power factor meter as well as the oscilloscope. We're going to see what power it's drawing, what the power factor is, and that's the essentially the phase shift. Yeah, we'll get into that. Down, apart, and back again. I got her back together. Place your bets down below in the doobly-doo as to whether or not she'll chooch. I'm about 80% myself. Even a blind pig gets a truffle now and again, yeah? Alright, so this is my power factor meter. Essentially, that's energizing the saw now. That goes down, saw is de-energized. We have watts, we have VA, and we have cos theta. The watts, of course, are power. The VA is apparent power. You just take the voltage in times the current. That gives us VA, and the difference between the two is our power factor. And that's critical in motor applications. We want to know the power factor, because otherwise, well, we need it to calculate actual watts. This VA doesn't really mean anything. It's not real. This watts is what we want. So we got 120 volts in, 0 amps. I built this power factor meter myself. If you're interested, there is a video about that, and you build your own. There you go. As you can see here, we're at 165 watts. 3.52, that's just windage, there's no load, so that's just the fan. If we look here, the VA is 435. And if we look at the power factor is absolutely horrific. Now, why would the power factor be so bad? I'm assuming it's because of that triac in here that's chopping up the voltage. Under load, that should come up quite a bit, and probably at closer to full speed, that power factor should come up, and the VA should be closer to the watts. Well, let's hit her again and listen to this thing growl. So we got her set down at 1. We're going to check the riffles here. $2,000 at 1. Now the question is, why couldn't they set the dial to 2,000 and 6,000, 2 and 6? Makes a sense to me, but I guess makes it too much sense. Holy, we're getting into some high-tech stuff here. Don't let it fool you. It ain't rocket surgery. We're just gonna walk through, nothing scary. For God's sakes, don't stop watching. Okay, safety first, right? We got the captain tape. I'm gonna tape up the ground lug so this is floating so I don't blow it up. Don't worry about it. That also means that this instrument is not grounded and the chassis could be at 120 volts and give me a shock if there's something wrong in there, but sacrifices must be made. It takes a while to boot up because the smarter things get, the slower they are. However that works. But this is the 1054Z, the new Rigol. Love it. I paid for it. It wasn't a freebie or nothing, no shill deal, but it's well worth the money at 400 bucks. I mean, you can't even get a Fluke 87 for that. However, I will say that the probes suck ass. I got the Tektronix as well. They're awesome, but these ones suck. Okay, so I just turned on some of the features here so we'll be able to see what's going on. See, Vmax is 172, but the root mean square of that is 120 volts, 60 hertz. So that's to the brushes. So that's to the motor rotor. Nothing going on there. There's no control going on there. So they must be controlling everything through the field winding. Okay, so now we've got the scope on the field winding. Oh, your favorite and mine. Please enjoy this brief intermission.
Alright, have some nitroglycerin right here underneath water to keep it more stable. You put a couple of drops right here on this piece of paper. Now hit it with a hammer to set it off. Like magic. Have an old master lock. I don't have a key to it and it probably hasn't been opened in several years. And so, today I'm going to open it with some nitroglycerin. Okay, now I got a little blasting cap that I made out of a old rifle casing. It's got gunpowder inside of it. And I got a sparkler to set it off. Sparkler's lit. Alright, see if I opened it.
And this here is Cody's lab. Plenty more where this came from. He is a rancher, miner, renaissance man, par excellence. I like his channel. You'll like it too. Check it out. Helps if you plug it in. Safety first, right? I unplugged it. Yeah, there we go. That's completely different. Let's have a look at that. You see it's chopping off. Hit the single there. Okay, we got the waveform here. As you can see, the max is still 176, but the root mean square is only 105 volts. If you look at this, it's chopping this up. So instead of getting the full AC to the brushes, it's clipping that, and if you average that out, we get a lower voltage. Okay, now we've got the scope hooked up to the field winding, and this is interesting because this is different than most universal motors. Well, this is what they call closed loop, and because there's a sensor in here, it knows what speed it's supposed to be turning, and it can check to see if it is turning that speed and then change a few little things to make sure it is turning that speed. And this is different because the motor rotor and the field winding are not in series, they're not in parallel, they're wired completely separately. And the Festool is controlling the field windings in order to get the speed and the torque that it needs. So we're going to see when we just checked the motor rotor, it was just straight AC, nothing happening to it. But when we check this field winding, we're going to see some interesting things. We'll start it off slow. And you can see it gives it full waveform until it gets up to speed, and then it starts to clip it. See that? And that coincides exactly with that grinding noise you can hear. Now we're going to speed it up. As you can see there, it clipped the waveform differently. So it's monitoring both the amperage and the voltage and clipping it to get the right speed out of the motor. And that's interesting because it will be able to compensate for load. Like when you're actually sawing, it'll maintain its speed, so it won't droop like a typical universal motor would. Well, we got the tracks all set up, and surprisingly it sticks real good. It's relying on the weight of the saw, of course. It's just got that neoprene foam, and yeah, it seems to work pretty good. So you'll have to, well, we'll take a cut. We'll be checking the power. You'll have to forgive my parallax error there. It's not VA, it's in watts. And then we'll switch it over to cos theta just to see the power factor while we're cutting. This is British Columbia's finest Chilean spruce, plywood 9/16. Now we got her set to cos theta. Same thing, 9/16. Of course, I don't have any dust abatement here in the shop, so I'm just filtering everything through a cigarette. And we're doing power factor on 1 1/8". Well, that was fun, but I mean, we got the scope. Might as well use it. Smoke them if you got them, am I right? And also, a lot of guys are saying, this isn't accurate, blah, blah, blah. So, I know for a fact this is accurate, so we're going to measure the current, and we're going to compare it to the current on this cheapo device. This is probably $1,500 instrument, and this is a, oh, I don't know, $35 instrument, something like that. Also from Spork Fun, I get a CT, a current transformer, and we're feeding that into the second channel of the O-scope, and that will show us the current. It's a little off, but if a picture is worth 1,000 words, then a movie is worth 1,000,000, am I right? Now this is not, don't tune out on me yet, stick with me. We're going to talk down in a language everybody here can comprehend. I ain't no rocket surgeon, so I'm not going to overcomplicate this. Just watch what happens here. I got a load bank, so we got 3 big 300-watt light bulbs, and one of these newfangled ones. I'm going to show you what happens when I turn this on. So, here we go. 2.1 amps, 2.23 amps, and on the current transformer, it's showing 3 amps, which is absolutely not even close to right. But the important thing is, well, and it's also out of phase, whatever. Ignore these little glitches, because what I want to show you is that the current is the same waveform as the voltage up here. 120 volts, 170 peak to peak, or neutral to peak, and this is the current. It's Nice and wavular. Now we're going to turn on this monstrosity instead. We'll turn this guy off, turn this guy on. Now look at the thing. So we can tell that there's some electronicals in there. There's some induction and some capacitance and all sorts of weird shit going on. Now if we change the load a little bit, you see what happened there? We got some more resistance. It looks a little more wavular. Sinusoidal, they call that. The top one's perfectly sinusoidal. This is fairly non-sinusoidal. So there we go. We got full court press on that with one nasty looking one on the end, and that's what gives us that. Now we turn that nasty looking one on the end off. Bingo bango. Now this is high amperage here. We got 6 amps on there, 6.5. We got 6.5 on there, and on the inductor we got, well, there we go, 6.5. However, there's some weird effects going on because of this, and I don't have this, blah 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 blah. You get the idea. Now we're gonna hook this up to this and see what it gives us. Right, I got into a bit of a nerdgasm there, and I forgot to point out that this is pretty close to this. Damn close. Close enough for the girls I go out with. That means to me that I am happy with the results here. However, if you look at it, it says 1400 watts. And the saw is rated for 1200, it says so on the name tag. So that is interesting. What we're going to do with this is we're going to connect this up to the field winding. We're going to see that this is getting chopped up, the voltage is getting chopped up, but we're going to see what the amperage is doing, the current into it as well. Alright, this is what I've been leading up to. We're going to do a heavy cut, 1 1/8 with this monster, and we're going to have all this electronical gear on here. Safety first, of course. Got some Chickens tape on there. What for keeping the 1s and 0s in. Don't want those magic pixies getting pissed off. Keep them nice and warm inside where they're supposed to be. Now I'm going to run this. And I got this set to a real wide time base, 20 seconds per division. So that's going to give us a snapshot of this whole cut. And we'll be able to see what the voltage is at the saw, what that confuser is doing in there, and also the amperage. It's not accurate as far as numbers go, but it's accurate as far as the look of it. So, if that makes any sense at all. Now let's be real about this. At this point, there's only me and you watching this video, because we're the only 2 guys on the entire fucking planet that are actually interested in seeing what the waveform looks like. But hey, dorks unite. Okay, that was a real nice snapshot, and we can see here, this is interesting. Right at the first one, I first pull the trigger, you can see that we're getting full AC, unclipped. Yoo-hoo! Oh, I moved it the wrong way. There we go. But there's no current yet. So it's trying, and then as soon as it starts getting current and it's coming up to speed, it starts clipping the waveform. And then this is, we're plunging here, and you can see the power goes right through the roof. We got an average of 13 amps. That's not to scale, it'll probably be more like 8 amps or so. But you can see the power come right up, so that's where we're plunging through. And we'll move that over. And there, it doesn't need nearly as much torque, so it cuts the voltage off. It clips that AC quicker, and we get less current. Less torque, less current, less torque. Now you multiply this instantaneously by this instantaneously, you get the power, and as you can see, we're getting fuck all for power at that stage compared to here at the startup and the first plunge through. So that is what the saw is doing electrically. This is the saw's EKG, and there's some neat stuff going on there, I think. Okay, we're going to check the inrush current on this bad mama jamma. I got a feeling it'll be quite low because it's got the soft start feature, right? Well, so that's really nice actually. Well, there you have it. That's the electronicals of this Festool TS55. It does make really nice cuts. It is a German engineer's wet dream. However, the build quality and the design, really not there. Not impressive at all. Not what you think. You know, you scratch the surface, it's hiding some nasty little secrets there. Not even close to the build quality or the thought as the Hilti tool that I took apart previously. The real question is this worth twice what the DeWalt or the Makita are worth? Only one way to find out. Keep your stick on the ice. Hey, thanks a lot for watching. I hope you enjoyed this Festool. I enjoyed taking it apart and going through, running it through its paces, seeing what's actually going on. And I gotta tip my hat to the guys that really enjoy the videos enough to throw a couple bucks in the pot. We couldn't do this type of thing without you guys, because nobody, and I mean nobody, is going to send me a free tool to take apart. It just ain't gonna happen, because ain't no manufacturer is going to send me a tool. So thanks, and a tip of the hat where thanks is in order. I'm going to do a follow-up video on this because I enjoy your comments, and there was quite a few on this Festool. There are some guys out there, I think their wives have Festool tramp stamps, because holy moly. So I didn't want to muddy the waters in this teardown with the rants. But in the next video, we're going to go over some of the good points that they came up with and some of the bad points. And we'll go over some of the errors I made, as well as a few things that I initially thought weren't too bad, but turned out after some thought are just horrific. I appreciate you sharing a little shop time with me and having a laugh. Thanks a lot. Keep your stick on the ice.